Hello everyone. In this video, I'll be explaining a few problems in the Laplace and Poisson's equation. Previously, we have seen problems where we were using Laplace equation and finding out V. From V, we were calculating E, which is equal to minus del V, right? And from E, you could find density, that is epsilon into E. So this was what we're doing in the previous problems. Now in this video, we'll be solving problems where the initial steps will be the same. You will be calculating the potential equation. From there, you will find intensity, then density. Okay. But after this, the next step is using density, we will find out surface charge density, that is equal to ds, the magnitude of d. Okay, rho s equal to d. And once we get this rho s, we are going to find out the charge value. Okay, the charge can be either taken as rho s into area if it is discrete, or you can find it as surface integral of rho s into ds in case it is continuous. Okay, and then once the charge is calculated, the next thing you're going to find is the capacitance value, which is charge by potential. Okay, so the problem in this video, we are going to see the problems based on this capacitor value, finding out capacitor value. So the first few steps are same as the other problems, and there are few more parameters which you have to calculate to get the capacitor. Okay, so we'll see how to do this using one example here. The question given is solve the Laplace equation for the potential field in the homogeneous region between two concentric conducting spheres with radii of A and B. The inner conductor is radius A, outer conductor is radius B. The potential boundary conditions are given. One is the potential is 0 at R equal to B. Other one is V is equal to V naught at R equal to A. So two boundary conditions are there. The question is to find the capacitance between the two concentric spheres. Okay. So as I told you, the starting part is same as the previous problems. Depending upon the data given, choose either Laplace equation or Poisson's equation. Here clearly they've given Laplace equation. So we start with del square V equal to 0. And the medium that is given is spheres, conducting spheres, which means it is spherical coordinate system. So in spherical coordinate system, what is the Laplace equation that you have to take? And as I've already told you, here the condition is given with respect to only radius. So take only the r part of that equation. The remaining two, that is theta and phi, can be ignored. Only the r component is required here. So I have taken the r component of the Laplace equation in spherical coordinate system. So then you have to simplify it. Simplification is you just have to try to eliminate the differentiation terms by integrating it. And every time you integrate, add an integration constant. Step by step, if you do, you can just check here. Okay, step by step. This is here after integration, I'm getting this answer. Integration constant C1 is added. Then this R square is taken to the other side. Again, I have to integrate on both the sides to get the final potential. So integration of 1 by R square will be minus 1 by R plus, since I've done integration again, I'm adding one more integration constant here. So once I get this expression, I have to use the given boundary condition to find the values of C1 and C2. Okay, the first boundary condition is V equal to 0 at R equal to B. So I've taken V as 0 in this equation and made R as B. And here you can just rearrange the terms and find out what is C2 in terms of C1. So I got this expression here. Okay, C2 is equal to C1 by B. I'll take the second boundary condition now. Second boundary condition is V is equal to V naught, where R is equal to A. So I'll put these values in the equation 1, and I got this expression. Now in place of C2 in this equation, I'll substitute C1 by B. Okay, this is this equation. So here in place of C2, I put C1 by B. So if I rearrange the terms and simplify it, I will get the equation for C1. So I got the answer for C1, which is V naught by 1 by B minus 1 by A. Now whatever I got for C1, I'll put this value here in C2 equation. That will give me the expression for C2 also. Okay, so I got both the expressions now. So both C1, C2 is determined. I'll put the C1, C2 values in this equation 1. And I will be getting this. Finally, I have the potential as minus V naught by R into 1 by B minus 1 by A plus V naught by B into 1 by B minus 1 by A. Okay, so I got the voltage equation. Next thing is I have to find out electric field intensity E, which is minus del V. So I have to take the gradient in spherical coordinate system and only the R component is considered because I have only conditions for R. There is no theta or phi in this. Okay, so I'll take this part of the equation. In place of V, I will substitute this and differentiate it. Okay, I've done the direct differentiation. You can just solve it yourself. This part is completely constant. So differentiation of this will give you 0. You have R only here, right? V naught by 1 by V minus 1 by A is constant, which can be kept outside. The differentiation of 1 by R will be minus 1 by R square. Okay, so this is what you're getting the answer for electric field intensity. And once you know E, you can calculate D, which is epsilon into E. And here they've not mentioned if it is free space or not. So keep the epsilon as it is. Okay. So then the next part, till here you have done even in the previous problems. Now what you have to do, the next thing, since you're supposed to find capacitance, capacitance is charge by the potential. So I need to know what is charge. Charge is calculated as rho s into area, surface charge density into area. So I need to know what is surface charge density. And surface charge density according to the boundary condition is same as the magnitude of flux density. Okay, if I take the magnitude of this, you see it has a direction AR, right? So I will ignore the direction and I will take only the modulus of this magnitude. So plus minus also becomes plus here when I consider modulus of it. Okay, so that hence I'm getting rho s as only epsilon V naught by R square 1 by A minus 1 by B. This minus can be multiplied here. This minus can be taken inside. So these two terms will interchange. Right? Minus of 1 by B minus 1 by A becomes 1 by A minus 1 by B. Okay. So just take the magnitude. Only this portion should be considered for rho s. And this rho s now can be multiplied with the area of the given system. That will give you the charge value. Okay. Now you see the spherical system is, what is given here is concentric spheres of radius A and radius B. And what path you have considered is somewhere in between these two, and I've considered the radius of that as r. So the area of this will be 4 pi r square because it's a sphere, not a circle. If it is a circle, it will be pi r square. But here it is given a sphere, right? So sphere is 4 pi r square. So area is 4 pi r square. And that gives you the charge value in coulombs. And once you get the charge, divide that by the potential. Okay. So here you can see that at A, the potential is, and the conditions are given. No? At A, the potential is V naught. At B, the potential is 0. So I cannot take 0 as the answer here. Anything divided by 0 will give me infinity. So I cannot take V is equal to 0 condition. I'll have to take V is equal to V naught and then substitute it here. Okay. So just take Q by V naught. Whatever is a Q value, divide by V naught. So V naught gets cancelled. So finally you have the capacitor value as this. Right. So it's very simple. Problem is very simple. First find out V using Laplace or Poisson's equation. From V you find E using this relation minus del V. From E you find D, which is epsilon E, and then rho s, which will be the magnitude of this, and then charge, which will be rho s into area if it is discrete in nature. If it is a continuous, then it is surface integration of rho s dot ds. Okay. And then finally, your capacitance value will be charged by the initial condition, the boundary condition, whatever is given. In that, whatever voltage is mentioned, no, that voltage you have to take. One of the condition will have voltage as 0, other one will have some other voltage value, not 0. That non-zero value should be considered here. Okay, this is how to solve the problems with capacitor. Okay. So we'll move on to the next question. Second problem similar to this. So they've given you the Laplace equation to find capacitance per unit length of a coaxial cable of inner radius A and outer radius B. Assume V is equal to V naught at R equal to A and V is 0 at R equal to B. So whenever they say coaxial cable, it is nothing but cylindrical coordinate system. Okay, it is cylindrical coordinate system. So for cylindrical coordinate system, since it is given only in terms of radius, take only the radius portion of the Laplace equation for cylindrical coordinate system. So that is done. And then simplify it step by step. You have to solve it to get the potential equation. This is your potential equation. Okay, and then use the two boundary conditions that is given. So one of the boundary condition is V is 0 at R equal to B. If I substitute that, I got C1 ln B plus C2 equal to 0. I can write C2 in terms of C1, so I'll get this expression here. Next, I'll use another boundary condition. I got this equation. Here, I will put this answer in place of C2. Okay, because I cannot take this 0 here. No? It's given as V0. So V0 is equal to C1 ln A. In place of C2, I will put this value. So that I will have equation only with one of the constant. It will be easy for me to calculate it. Okay, so I have this expression. Now C1 can be taken common, and by rearranging the terms, I will get the answer for C1, which is this, V0 by natural log of A by B. Then I will put this value in C2 equation to get the C2 answer. Okay, and once I get C1 and C2, both of them can be substituted back in the first equation to get the final expression for potential. Okay, and once you have the potential equation, the next thing is intensity, which is minus del V. So again, you have to use a gradient equation in cylindrical system with only the radius part. Substitute in place of V this equation, solve it, differentiate it, simplify it, you will get the expression for E. And then D will be equal to epsilon into E. So just multiply by epsilon. They have not mentioned anything about free space here. So just keep epsilon as it is. And once you get the D value, magnitude of that will be your surface charge density. Okay, again you see you have a negative sign here. Right? What they have done here is that minus is multiplied with the natural log with them. And you should know this minus natural log of, if I have x by y, if I have to remove the negative sign, what I have to do is I have to interchange this. If I interchange this, minus can become plus. That is what is done here also. Natural log of a by b minus natural log of a by b is made positive natural log of b by a. By interchanging this, we will be able to remove that negative sign. Okay. So we got the surface charge density. If I multiply the surface charge density with area, I will get the charge. And this time you have a cylinder. So cylinder area will be circumference into length. So 2 pi r into length. That is what is done here. And once you get the charge, divide that by the potential, initial boundary potential, that is V0, to get the capacitor value. Okay, so this is how we find capacitors for the given problem, capacitance value. So Q by V0. In this particular question, they've asked you to find capacitance per unit length. Okay, capacitance per length. So if it is per length, you have to divide this capacitance value by 1 meter, unit length. No? So you have to divide it by 1 meter. So I have to assume that the length value is equal to 1 meter. And by that, you are getting the equation for capacitors per unit length. Okay, so this is the second question. Similarly, you have to go for the third problem. Two plates of parallel plate capacitors are separated by density and maintained at potential 0 and V0 respectively. So again here, as you can see, they are saying there are two parallel plate capacitors. The distance between these two is T. Okay, and one of them is at 0 potential, other one is at V0. Assuming negligible fringing effect, determine the first part, potential at any position between the plates. So for this initial part is same as you're finding out potential value. Whichever coordinate system is mentioned, in that coordinate system, you have to get the Laplace equation with respect to only the given axis. Okay, here they're given the distance between the two plates. I can assume that the capacitor is placed in Z direction. So I can say the distance can be taken in Z direction, right? So I will take only the Z component, Cartesian system Z component. So dou square V by dou Z square equal to 0. By simplifying this, I got this equation. Now they have not clearly given the condition here. In statement they have given, so you have to write down the conditions. They are saying that the potential is 0 at one end. So I can say the potential is 0 when Z is equal to 0, initial one, the lower plate. And the potential is equal to V0 when Z is equal to D. So I can take these two conditions and simplify it, find C1 and C2. Once I get C1, C2, I'll put that back in this main equation and I got the potential value as this. So So first part of the question where they're asking to find the potential is done. Okay. The next one is, in the second part, they're asking to find surface charge density on the plates. So to find surface charge, I need to know D. And to find D, I need to know E. And E is nothing but minus del V. So first you're going to do this operation minus del V in Z direction, the gradient equation for partition system. By that you got the E value. And by multiplying by epsilon, I will get D. And by taking magnitude of this, it gives me rho S. Okay, surface charge density. So again, magnitude, I can just take it to be a positive value. So once I get this, rho S is multiplied by area. Okay, just check this one step by step. So here what they've done, they've taken rho S as the modulus of D or magnitude of this. If you remember, we do this, right? If I have a vector like this, x ax plus y ay, how do we calculate the magnitude? Root of x square plus y square. So same thing is done here also. You have only z component, so it is root of minus v naught epsilon by d the whole square. So the square, if I do the square of this, I'll be getting positive v naught square epsilon square d square. I'll be getting like this v naught square epsilon square d square. Minus becomes plus. And the square root of this will give me v naught epsilon by d. That is how we got this equation here. Okay. So once you get rho s, the second part is done here. Rho surface charge density is calculated. The last one is capacitance between the plates. So for finding out capacitance, you need to know the charge value, and charge is nothing but surface charge density into area. And we don't know what system is mentioned here. So I'm going to write the area as A, denote the area as A, because I don't know what type of system it is. So I cannot find the equation for area here. I'll just keep the area as an alphabet A. So by substituting that, I got this charge, and charge by V naught will give me the capacitance value. Okay, this is the equation for parallel plate capacitor. Right. So we'll move on to the fourth problem under this. Again, conducting spherical shells with radius A and B values are mentioned now. It's again spherical coordinate system. It's maintained at a potential difference of 100 volt at R equal to such that V of R equal to B is 0 and V of R equal to A is 100. They're given the conditions. And when R is B, potential is 0. When R is 100, when R is A, potential is 100 volt. These are the boundary conditions. We're supposed to determine V value and E value in the region between the shell, and epsilon R value is given here. So just have to find out V and E. Also determine the total charge and the capacitance. Okay, so first we'll start the potential spherical system, and conditions are with respect to R. So take only the R component, simplify it, get the equation, and then use the boundary conditions to find C1 and C2 values. And once you get C1, C2 values, put it back in the main equation to get the potential solution. Okay, so V is done. And to find, you can just pause the video and check the steps. Okay, you can check and solve it yourself and see if you're getting the same answer. Right? And once potential is done, you can find E, which is minus del V. So minus del V minus dou V by dou R of in AR direction. This is only the R component of gradient equation in spherical system. So that by solving this, so by solving this equation, you will get the E value. So V is done, E is done. Next, they asked you to find charge. To find charge, first to calculate D. In this case, they have given the value of epsilon R. So if you want, you can substitute that value. Here that capacitors, but if you want, you can substitute epsilon as epsilon naught into epsilon R. Epsilon naught value, you know, 8.854 into 10 power minus 12 into epsilon R is given as 2.5 in the question. Okay, you can substitute those values and simplify it, right? So that will give you rho S. But now to see the rho S equation, we have 15 epsilon by R square, right? So it's a continuous system. If it is continuous surface charge density, I cannot just take rho S into area. I will have to do integration now. Okay, so integration is nothing but surface integral of rho S dot ds. And this is spherical system, and you are taking in R direction. So for spherical system in AR direction, the surface area will be r square sin theta d theta d phi. Okay, so take the dot product of this. Just multiply the scalar value with this. R square gets cancelled. Integrate with respect to theta and phi. For spherical system, you know the default value of range of theta and phi. Phi will be 0 to 2 pi, theta is 0 to pi. So by substituting it, simplifying it, I'll be getting the charge value as this. Okay. And then once the charge is given, a charge is found, capacitor will be Q by V. Again, I told you there are two values for potential. One is 0, another one is 100. You cannot choose 0 because you get infinite capacitance. You have to choose the value as 100 here. Okay. So by substituting that and simplifying it, you will be getting the capacitor value, which will be 41.72 picofarad. Okay. So I want you please solve all these questions yourself and check if the answers are correct. If you have understood the procedure, it is quite easy. Okay, all the problems are similar. Let's move on to the next one. Find the potential function and electric field intensity for the region between two concentric right circular cylinders. Whenever you see cylinders or coaxial cable, it is a cylindrical system. With conditions, boundary conditions are given here. Epsilon R value is given. Find the surface charge density rho s and determine the capacitance C per meter length. Okay. So again, start off with del square V Laplace equation for cylindrical coordinate system in R direction. Use boundary conditions. Find out C1, C2. Substitute it back in the main equation to get potential. From potential, next is electric field intensity minus del V. The substitution, you are getting this. And then from E, it is D, which is epsilon E. Got this equation. Okay. And from D, it is magnitude of D will give you rho s. And again, you have an R component here. So we are going to do the integration. And we are taking in R direction. So it should be R d phi dz. Okay. Substitute that to the integration. And here phi is 0 to 2 pi. For z, limit of z, you can check the question. They're given the data will be R is equal to 1 millimeter and R is equal to 20 millimeter. So here you can just take the values of z, the length of this as 0 to 2. Okay. Even though the cylinder is given as at one particular point, the range is considered as 0 to 2. Sorry, this is not 2. Sorry, this is z because we don't know the length of the cylinder, right? It's given as z here. So 0 to z, not 2, it's z. Just keep the z value as it is, length as it is, because we don't know what is the length of the cylinder. So once you get that, you have charge in terms of z itself. Then take the ratio of charge and potential. That will give you the capacitor value. Now again, potential is not starting from the location 0. Right? It is not starting from radius 0. They are given in between values. It is given from 1 millimeter to 20 millimeter. In between this region, I want to find out the capacitance, right? So what you have to do, take the potential difference between these two. So previous problems, what was happening is they had given you one of the value as of potential as 0. Other value would have been given as V0. If I take the difference of these two, V0 minus 0 will give me V0 itself. That's why I wrote here as V0 in the previous problems. But in this case, both the potential values are not 0. Okay, so I have to take the difference between the two potentials. That will be your V here. Okay, that is what is done. I have to take the difference of V at R equal to 20 millimeter minus V at R equal to 1 millimeter. So if I take the difference of these two, as you can see, the potential at at 20 millimeter, it is given as 150. At 20 millimeter is given as 150 and at 1 millimeter is given as 0. So 150 minus 0 will be 150 volt. Now suppose they had given you 150 and instead of 0 if I had given you 50, then your difference would have been 100. So we'll have to substitute V is equal to 100 here. Okay. Take the difference of potential between the two boundary conditions. If one of them is 0, then no problem. The other value will be your default answer. But in case if both the values are not 0, then you will have to take the difference between the two and get the answer before you substitute it. Okay, so this is the capacitance value, and now they are asking you to find capacitance per meter length. So the length of the cylinder can be assumed to be 1 meter. So from there you will get the value of capacitance. Okay, so this is how the problem is done. Coming to the last question, is slightly different. It's not like a proper numerical, but it is a derivation kind of problem. Okay, so with this we'll be finishing the capacitance value, capacitance problems. So last problem, a capacitor has square plates, each of side a meter, and the plates make an angle theta with each other. So there are two square plates, okay? One of them is placed at the origin or x equal to 0. The other plate is at some other distance, okay? So this is one plate, this is one plate. Both the plates are of size a meter, okay? The side is a meters. But the one of the plate is making an angle of theta with respect to the other one. That's why the upper plate is slightly tilted, and the angle by which it is tilted is given as theta. This is your upper plate. This is a lower plate, and this upper plate is making an angle theta with respect to the lower plate. Okay, and the question is to show that for small angles, small theta, the capacitance equation is so and so. So I have to derive the equation for capacitor, and I have to see whether this is the answer I'm going to get. Okay. So here to start off, the diagram will not be given in the question. This is drawn. This should be drawn by you. So consider one of the plate, the lower plate, at a potential equal to 0 volt, and upper plate is at some other potential V dash. This is you have assumed these values. We are assuming that the lower plate is at 0 value and the upper plate is at some value that is V dash. And the upper plate is making an angle theta with respect to the lower one. Now let the potential of upper plate be V dash at the center of the plate. That is, if this is A, then at the center, the distance, the point is going to be x-axis value will be a by 2. Okay, this is your x-axis and this is y-axis. So in x direction, if this is a center, if I drop a line from there, this distance becomes a by 2. And this distance that is up to this point is the y-axis value. So y-axis is going to be, let's assume that the distance between these 2 points plates are d. Along with that, I have to add this portion also, right? So this distance is d. I need to know what is this portion. This plus this totally will be the y-axis value. Okay. To know this small distance, we'll take the help of this right angle triangle. So this acts as opposite and this is adjacent and this is hypotenuse. So what I can do is I'm taking really this portion and I want to find out this value distance. I need to know what is the value of this point. So here I have a by 2. I have theta. So can I take tan here? Okay, once again. So I can also take this as a by 2. Half of it. No, if it's the middle, then this portion will be half. Your hypotenuse. This is opposite. Let me call it as d dash. Okay. So d dash can be written as, if I take opposite by hypotenuse, d dash by a by 2 is sine theta. See why I'm taking sine theta is, we'll see. I'll tell you later because I need this theta value here, right? So d dash is going to be a by 2 sine theta. So this portion of your length is going to be a by 2 sine theta. And the remaining is considered to be d. So total y-axis value will be for the middle of this second plate. Y is equal to d plus a sine theta by 2. Okay. So at x equal to a by 2, the potential is 0. And at y equal to d plus a sine theta by 2, the potential is v dash. Okay, now we'll start with Laplace. I found out the two initial boundary conditions. Now I'm going to start with Laplace equation. And here we're going to take it in terms of the perpendicular direction is y. The perpendicular direction to the plates are y. So del square y is equal to dou square v by dou y square equal to 0. So simplify it in the same way you have done before. Do the integration, add the integration constant, get the expression for potential. Now the first one is going to be when y is 0, potential is 0. Right? When the distance, and I'm at the origin, the potential is 0. I'll substitute this to get the constant. Another boundary condition is when y is d plus a by 2 sine theta, the potential is assumed to be v dash. So I will use this boundary condition in this equation to get another constant c1. I'll substitute both of them back in the main equation. So I finally got the potential equation as 2v dash by 2d plus a sine theta into y. Okay. Next, after potential, it is electric field intensity minus del V. So again in y direction, I have to differentiate this with respect to y, and I got this answer. And then D will be epsilon into E. So epsilon naught, as you can see here, you're using epsilon naught, right? Free space. So directly you can take epsilon naught here. So you got the D value. And rho s is going to be just the magnitude of this. Okay. So magnitude will be only one direction, no? Root of square of this. So positive, negative sign becomes positive, and square root will get cancelled. You'll get this answer. Okay. And charge will be rho s into area. So rho s is already there. You have calculated from here. Area is you have a plate. Okay, with the side A. Another plate with side A. The area is going to be this side square. So A square. Okay, area of the plate will be A square. Once you get Q value, next capacitance is Q by the potential. So here this potential is nothing but difference between the potentials at 2 points. At one point it is V dash, other point it is 0. So V dash minus 0 will be V dash. So by substituting that, this V dash gets cancelled, and this is the equation you have now. Next, what they've done is they've taken epsilon A square outside, and in the denominator they've taken D as common. So if I take D outside this, or 2D outside, now see, this is the equation you have, right? Next step, what they've done is 2 epsilon square, epsilon into A square divided by 2D is taken outside. Here you have 1 divided by, if I take 2D common, 1 plus, it becomes A sine theta divided by 2. Okay, if I take something common from the numerator, it should be divided by the denominator in the next term. This 2 gets cancelled. That's how we got this expression here. Right? So if you now look at this, you have this power series, series expansion. 1 by 1 plus x can be written as 1 minus x plus x square minus x cube plus x power 4, so on. Okay. Same concept is applied here. In place of 1, you have 1. In place of x, you have this value. In case of x, you have a sine theta by 2d. So if I apply the similar series expansion to this, I will be getting 1 minus a sine theta by 2d plus a sine theta by 2d the whole square minus a sine theta by 2d the whole cube, and so on. And since they have told that theta is a very small value, higher power terms can be neglected. And I will take only the first 2 terms, 1 minus x. So in place of x, I have substituted this. So this is the equation I got. So I'm going to replace it in the capacitor. Instead of 1 by 1 plus this value, I have replaced it with the series expansion. And now you see that the total theta is small. So whenever you have a very small angle, the sine theta value can be approximately written as theta itself. So do you know what is sine 0? Sine 0 is 0, right? If I take any other small value like the sine of 10 degree, okay, so let's just see what is the value of sine 10. Just do it in the calculator, we will find sine of 10 degree is sine of so we'll be getting something as 0.1736. If I take even smaller values for theta, 7, 5, so if you take very small values of theta, no, you will find that it will be approximately equal to the theta value itself. For the best example is if you take sine 0. Sine 0 is it's 0, right? 0 is the smallest value you can get for theta here. So sine 0 is 0. So we can do this approximation for theta. So sine theta is approximately equal to theta. So in place of sine theta, you are going to replace it with theta. So now if you see, this was the equation given in the question, and they had asked you to prove that the capacitance value will be this. Okay. One more thing, when theta is small, cos theta can be written as 1. If you have cos theta in the equation, when theta is small, cos theta becomes approximately equal to 1. Sin theta will become approximately equal to theta. Okay, because they are talking in terms of, uh, when I say small, it is actually close to 0 value. Okay, that's when you can, that is when you can actually use these approximations when theta is approximately equal to 0. Okay, so this, with this we have completed the problems, all the types of problems under Laplace and Poisson's equation, and this completes your module 3 first half. Okay.